Okay, off we go. So here's where we're picking up from. I'll say last time, but y'all watch these videos on your own. An example. Now let me remind you what we're doing an example of. We're doing an example of this theorem right here. Technically, it's this theorem here. That says that if a vector field is a gradient, this is specifically a three-dimensional vector field, if it's a gradient, that will be simultaneous with, or said differently, you can detect this by the curl being 0. Okay, so you want to compute the curl of your vector field, see if you get 0. Either you do or you don't. Okay? So here we go. So is this vector field here a gradient? Again, the question is this, and we're going to resolve it by looking at that. Okay, so we compute the curl. And let's see here. There's several components of the curl. First coordinate, second coordinate, third coordinate. You'll notice I didn't compute all of the coordinates. And beautiful little convenient little bit of cleverness is that if the reason you're computing curls because you need to know if it's 0 or not, as soon as you find a non-zero, color choices, as soon as you find a non-zero coordinate, game over, right? I already know, just on the basis of one non-zero coordinate, that this is definitely not the 0 vector. Now, it might be that these last two coordinates could be 0. It's possible. It doesn't matter. Right? On the basis of that one coordinate alone, I know that this is not 0. Going back up to the theorem, this means that this vector field does not have curl equal to 0, and therefore it is not a gradient of anything. Is that cool? Is everybody happy with that? Okay. All right, two-dimensional example. Here we're using, you can see here, two-dimensional vector field using this first theorem that we saw up here. And again, how do we tell if we have a gradient? This time it's curl, this being the scalar curl, right? Two-dimensional curl is a scalar, three-dimensional curl is a vector. It's weird. That's the way it is. So let's check and see. Let me erase this. Let's check and see. So we compute the curl by the usual formula. There is the formula for curl. It is not 0. So no. Again, also not a gradient. How are we doing? All right. Now, just for sort of like, intuitive satisfaction, let's just play a little thought experiment here. What would it look like if this were a gradient? Our vector field, this is a vector field we can draw a picture of. And it looks like this. If that were a gradient, and keep in mind, gradients point uphill, right? If this vector field were a gradient, gradients pointing uphill, that would mean, hypothetically, all of these vectors would be pointing uphill. And that would be a pretty weird mountain to try to climb. Right? You just keep going around, up. You keep going up. And isn't that like a Greek myth or something? Sisyphus. Yeah, exactly. So, nonsense. Right? There's absolutely no way. We can kind of even see it from the picture. That there's no way that this could possibly be a gradient. And by the way, a thought to plant for your consideration is that if we wanted to get a little bit more precise about how would we make this point, we could talk about, well, yeah, I can actually count how much my altitude moves uphill by computing line integrals like this. And so this business about curl answering a question for us relates to line integrals. And so you see we're kind of getting some connections between Green's theorem and the fundamental theorem of line integrals. So just, for your consideration, something to be chewing on. Okay. All righty. So moving along, this next little bit is something I like to throw in. This is not in the book. This is a really tough thing to talk about. Ultimately, what I'm about to show you is some glimpses of a bunch of math that's way above Math219. Can't really tell you the whole story, wouldn't be appropriate. But the tragedy of that is that there's some super cool ideas in there, and it's not all just, mathematical formalism. Right? So even if you get rid of all the mathematical formalism and rigor and all this kind of stuff, there's some tremendously useful, valuable, intuitively helpful patterns and analogies that you can notice just by thinking about, again, strip down all the formalities off of that sophisticated stuff I'm not going to show you. And roughly speaking, this diagram and a little bit more expanded version of it that I have here are what remains when you strip off all that sort of formal rigor, that kind of stuff. By the way, this file that we're looking at, this is a PDF page, and it is available in let's see here, it is in, I want to say it's on the class website. I think there's a folder called Class Materials. If I remember correctly, that's where it is. It's either class materials or course materials. I don't remember which one. But anyway, y'all can get a copy of this. So let me talk through a few things about this diagram. Some of it I'll do in the sort of the compact version here in the notes. Some I'll switch to the other page. You can take these operators, gradient, which takes a function and returns a vector field, and curl, two-dimensional curl, by the way, that takes a vector field and gives you a scalar valued function. And you can compose them like I have drawn here. And you may recall I made a reference to this back in chapter 3, that you can compose these operators kind of like this. So I'm going to start showing you a couple of things about why this is useful and we'll have a little bit more context now for why it kind of sort of makes sense to do this, because we've developed more about curl and more about gradient. So first thing I'm going to mention, I'm going to kind of remind you that this is an exact sequence. I may have used that term back in chapter 3. This is just this is the sort of proper way to say what I said back in chapter 3 as everything has a lifetime of 2. Right? So you may recall, for example, if you take a function, you compute its gradient, that gives you some vector field. Well, that vector field, its curl will be 0. Right? So that has a lifetime of 2. Right? Birth, survival, death. Again, it's just a metaphor. Don't take it too seriously. Likewise, if you have a vector field, and if you compute the curl, and if you get 0, hypothetically, let's suppose that happens. And then you ask the question, hey, is there an anti-gradient? In other words, if I were to, actually let me do it like this. Anti-gradient, going backwards, if you will, through the gradient arrow. I want to know, is there some function whose gradient is that original vector field? Well, let's just kind of think it through. If there weren't, right, hypothetically, if there were no anti-gradient, that would mean that this is the entire story right here, and that would mean that this vector field had a lifetime of 1, and again, that's not how it works. Everything has a lifetime of 2. Always 2. It's weird, right? So that means there can't not be an anti-gradient, aka there must be an anti-gradient. So kind of a cool conclusion that you get there as well. So neat facts. Now you can just remember these facts as statements of algebra, right? Independent theorems that you write down. The condition for there being an anti-gradient is blah blah blah, and if you have a gradient, then what is it that we know must be 0? Well, it's curl, and you can just memorize those facts. I find that harder to digest and I find it easier to forget. Right? So I find it very satisfying to just remember that these operators compose in that order and that it's an exact sequence. And then the structure of the way I've pushed them together does the remembering for me. So I find that helpful. Okay. By the way, let me switch to the other diagram here. You could imagine integrals that we compute of these different things. And by the way, I use these headers up here as an indication of what dimension are we talking about. Oh, yeah, question.
I'm a bit confused because so when we apply the del operator like to the function, are you saying
it's a gradient.
So so you're saying it's giving us a vector field?
Mm-hmm.
Like, are you saying the vector field is equal to the gradient here? Or?
No, what I'm saying is that if you have a function and if you compute its gradient, then the result is a vector field.
Okay.
Yeah.
So we're not just adding the del operator. So you're saying, okay.
This is an operator that applies to one of these
function.
and produces one of these.
Okay.
Yeah, that's all I'm saying. Yeah, sure. So let's think about the dimension here in the two-dimensional world. If I wanted to do a two-dimensional integral of a vector field, of a function, aka if I want to do a double integral, what's my domain? Well, my domain is a two-dimensional region. And if I were to say, hey, I've got a vector field and I want to do a one-dimensional integral of that vector field, what construction do we know? Like, what is that? Well, that's a vector line integral, which we do over curves, right? Specifically oriented curves. The zero-dimensional case is technically, if you open your mind a little bit, if you broaden the definition of integral by a little bit, it is actually kind of a reasonable thing to view just the mere evaluation of a function as a kind of an integral. It's a really weird, anomalous little kind of an integral, but you can view it that way. And of course, we evaluate functions at points. So here's the neat additional observation. Two-dimensional regions have boundaries that are curves. Curves have boundaries that are points. And this sequence, too, is kind of exact. There's a little asterisk. It's not. There's a little counterexample, and there's ways to fix it, and it can be dealt with. For approximate purposes, first cut purposes, this is also close enough exact in the sense that if you have a two-dimensional region, now this is a geometric appeal. If you have a two-dimensional region, and if you look at its boundary curve, the boundary of that is nothing. Right? Two-dimensional region. Let's say it like this. If you have some area of land and you put a fence around it, that fence neither starts nor ends. If there was an end to the fence, that's where you get out. Right? It wouldn't be a boundary. Does that make sense to everybody? It's kind of a geometric appeal. Okay. All right. Okay, let's see here. Back to here. Let's talk about the pattern of the theorems. Wrong page. Here we go. Back to here. Let's talk about the theorems that we've discussed. We've talked about Green's theorem. Here's the way I like to think about Green's theorem. Reminder, if you have a vector field, you can apply curl. By the way, I created this document back when I was still pushing this GRN notation. Just remember, this is just an alternative for curl. When you see GRN, just think curl. So, you can compute curl of a vector field, and you can talk about the boundary curve of a region. And one way to say Green's theorem is that if you have a vector field and you compute curl, if you have a region and you look at its boundary, that the line integral of your original vector field around your boundary curve and a double integral of Green's operator on your original domain are equal. Right, so this is just kind of a diagrammatic manifestation, maybe you might say, of Green's theorem. I'll write it in green here. This, that, same. Right. So this is, very quick and dirty. Sort of what does Green's theorem look like on the diagram? It looks like about like this. And now let's talk about the fundamental theorem of line integrals. The fundamental theorem of line integrals says that if you take a gradient of some function, and if you look at the boundary, namely the endpoints of a curve, and if you're interested in the line integral of that gradient over the original curve, like so, and if you evaluate the original function on those endpoints like so, then again, you get the same thing. Or again, just for sort of efficiency purposes, that. So this is kind of a shocker to notice, but even though these two theorems, they seem like they're about totally different things. Green's theorem is about line integrals being computed with double integrals when I'm looking at a two-dimensional region and its boundary curve. The fundamental theorem of line integrals is about change, which I can either compute with or use to compute a vector line integral. They seem like they're pretty different, but the pattern is shockingly similar. Everybody notice that? Okay. So this is something that first got noticed a long time ago, right? We'll see. The theorems started getting written down a couple of hundred years ago, and I'm pretty sure that they very quickly noticed, hey, wow, these are really analogous theorems. But they weren't able to figure out, mathematicians didn't work out for sure that in fact these are related theorems until the middle of the 20th century. And the way I like to say it, this is a true fact, just to emphasize how recent and modern this math is, I knew people who knew the mathematician that figured that out. Right? It's very modern, right? It's recent. It's very sophisticated math. By the way, it eluded the great 19th century mathematicians like Gauss, for example, never figured it out. So it's very sophisticated stuff. So what we're seeing here is a glimpse into this larger truth, this larger deep mathematical fact that these two theorems are actually special cases of a single all-encompassing theorem. It's not that they are coincidentally analogous. It's that they're the same theorem in different contexts. So anyway, now I've left out a tremendous amount of details, right? And this is not the class to go into those details. It's just not appropriate for this level. But I think it's culturally useful, right, for y'all to know that, hey, yeah, this is not a coincidence, and yes, there is a deep connection. And by the way, the tools that you use to prove the connection between these two theorems are some sophisticated mathematical constructions that are what I've boiled down, taken out all the rigor and all the sophistication to produce this diagram. Right? So that this diagram, in some sense, is kind of a glimpse into where that sort of all comes from. So I think that's kind of cool. The other thing I like to point out is I'm a big fan of analogies, just from a kind of a learning standpoint, kind of a comprehending standpoint. Analogies are super valuable because if you understand, let's say, one of these theorems, right? Maybe you feel like you have a good understanding of the fundamental theorem of line integrals, but you're kind of creeped out by Green's theorem, let's just say, hypothetically. Right? The fact that they are so analogous gives you an opportunity for how you can use what you understand about the left theorem to help you understand what you're missing about the right theorem. For example, the role that the gradient plays. What's the deal with the gradient there, right? Well, you probably have some intuition for how gradient is a way of keeping track of how a function is changing. You can kind of see there's a sort of a connection there, right? That this operator that produces this vector field is an integrand that relates to what's being computed on the left. Well, in exactly the same way, right, there's this analogous role that curl plays. Curl, namely that operator, namely this function that we use to take a double integral of, is in its way keeping track of what this accumulating quantity is, namely circulation. Right? So very strong analogy there. So to whatever extent you feel like you understand what's going on the left, look on the diagram, see what the analogous player is over here on the right, and that is your clue for how to help yourself understand that. So I think there's a huge amount of potential in a bunch of different ways that y'all can use this to your advantage. Okay. All right, let's see. What have I... no, I remember, but I'm going to switch back here just real quick. Yeah, okay. So let me talk about some special... Oh, wrong. Let me talk about some special vector fields. There are certain special vector fields. And again, the diagram is going to be really helpful in keeping track of the various properties of these special vector fields. And these special vector fields are special in how we take vector line integrals of them as follows. The vector fields in question are gradients. Vector fields that are a gradient of some function. And we've actually already seen some of the properties that these gradients have. Gradients have the feature that, for one thing, curl is equal to 0. Right? And the other one that we've talked about is, and this is a little harder to put on the diagram, so again, just keep in mind, this diagram, there's nothing rigorous going on here, right? This is just my attempt to attach some locations to some concepts just for sort of mental organization purposes. So I'm going to represent path independence as follows. Path independence means if I have two curves with the same boundary points, start and end at the same point, then they will give you the same values of a vector line integral of that vector field. Right, so that's the way I like to draw path independence. So, okay, who cares? What does this do for us? What this is going to do for us, and actually let me give myself a little bit more space here, and I'm going to scroll real quick down to here. Notice we have a three-dimensional diagram here. We haven't talked about a lot of the stuff on this diagram yet. The three-dimensional, kind of chapter 7 is where we're going to really start developing the big ideas in this three-dimensional diagram. But it's totally analogous to the two-dimensional one. And here's the cool fact. First cool fact, I should say. This pattern of relationships between two-dimensional vector fields, the special two-dimensional vector fields, call them whatever you like, gradients, irrotational, path independent. We're all talking about the same vector fields, right? The exact same relationships hold in 3 dimensions. And here's where it gets really weird. If you move up a dimension, everything still works. Now, this cannot make sense to you right now because we, again, haven't talked about a lot of the stuff going on in this diagram. So, for example, we have not yet even talked about what that is, right? We haven't talked about, it's going to turn out this is something called a vector surface integral. And it'll be coming soon, probably not today, probably on, is today Friday? Probably on Monday. But, we're 2 seconds, we're going to find that there are some special vector fields in relation to how we compute this thing that we're going to call vector surface integrals. And being a curl is going to be simultaneous with divergence being 0. and is going to be simultaneous with this weird property that we haven't even had a glimpse of this yet, that when you have two surfaces with the same boundary curve, they will always give you the same value of a vector surface integral of one of these special vector fields. And you could probably take a reasonable guess as to what we're going to call this orange property. Anyway, so I think it's shocking how this pattern holds even in different dimensions and even shifted over and totally different features, right? Divergence didn't come up at all in the two-dimensional case of, we're talking about these special vector fields. Completely different properties, but they have all the same pattern. And this pattern only shows up when you view these properties on this diagram. And again, tremendously helpful. You are going, I hope, if you, follow the diagram and kind of take a diagrammatic, keep track of all of the ideas as we develop them from the point of view of this diagram, you're going to find it easier to understand why surface independence relates to divergence being 0 if you take this point of view and think analogously about why path independence relates to curl being 0. All the same ideas, just dimensionally, just geometrically different. I'm sorry, yes, you had a question.
You mentioned that path independence is basically when we have the same start and end points, and then the vector line integral will be equal for both.
Yep.
However, further up, we had an example where that wasn't the case.
Yeah, so I'm not saying that all vector fields are path independent. You're quite right. They're definitely not. I'm saying that there are special vector fields that have this property.
So even if we do have the start and end points, it's not necessarily path independent.
See, that's right. So we're talking about two different things, right? So curves may or may not have the same starting and ending point. The thing that has the feature of being path independent is the vector field.
Okay.
Yeah. Right. That's right. So if a vector field is path independent, then we can have this conversation about paths and starting point and ending points, and everything will work out. But most vector fields are not path independent in the first place, and then there's just nothing to talk about.
Okay. Thank you.
Yeah. All right. So neat stuff. Powerful ideas, and again, really unfortunate this isn't in the book. It's not in most books, but I just think this is really good stuff, and I hope you'll find it useful. Okay, so moving on now. Let's talk about antigradients. Just a reminder, the reason we need antigradients is because they come up with the fundamental theorem of line integrals. You want to compute a vector line integral? Fundamental theorem of line integrals is awesome for that, but you got to find that function whose gradient is your vector field in question, right? So being able to find an antigradient is extremely useful. Now, in the examples that I showed in the recordings that y'all watched while I was out on Wednesday, in those examples, I just pulled a rabbit out of a hat and said, here it is. Here's the antigradient, right? No evidence of how I came up with that antigradient. Just here it is. And you can check that it works. But how did I get it in the first place? Right? Or more importantly, how are you going to get it when you need to apply the fundamental theorem of line integrals, and therefore you need that antigradient? So here's the big idea. If a vector field is a gradient, well, that vector field has coordinates. Being a gradient of something means it has coordinates, and that would mean the coordinates would have to be equal, and so therefore we get these three equations here. Okay, so what? Here's these are statements about partial derivatives. And of course, anytime you have a statement about a derivative, you can sort of phrase it, grammatically, kind of turn it around backwards, however you want to say it. You can rephrase that as a statement about antiderivatives. So that's all that's going on here. These are just all the same statements, just here in terms of partial derivatives, here in terms of anti-partial derivatives. Okay. But remember, when you talk about antiderivatives, you always have to say plus c. Now let's take a quick moment to remind ourselves, why do we say plus c? Well, we say plus c because this thing, its job, right, the whole purpose of an antiderivative is that when I take the derivative, I want to get a particular certain thing. So I just need the derivative to be a certain thing. So the whole reason that I have to say plus c here is because that plus c, when I take the derivative, I get 0. In other words, this constant doesn't matter. Right? So this flashback to single variable calculus. Plus c because it doesn't matter anyway. Well, here's the thing. What are the functions that when I take their x partials give me 0? What are these things that don't matter? I can add them in for free because they don't matter because their partial is 0. Well, frankly, not just constants anymore. Now, anything that doesn't have any x's in it. Any function of y and z. Take the x partial of this expression that has only y's and z's. The x partial is 0. It doesn't matter. You can add that in for free all you like. It doesn't make any difference. Right? So when we talk about anti-partials, you don't add a constant. You add what we call a partial constant. It's actually a function. But it plays the role that in single variable calculus is played by a constant. Okay, so reminder, we're trying to figure out if this could equal to this. So we're trying to figure out if these could equal to these. AKA, we're trying to find, is there some function that's equal to, that's going to satisfy all these equations? Well, we're trying to find some function that's equal to all three of these things. And this is the point of view that's going to allow us to actually find these things. We're going to write down all three of these things, and then we're just going to look at them and see, is there a single function that's equal to all three of these things? And that's easier to see in action, so let's just do one. Here we have a vector field. I want to find an anti-gradient. Following the rule above, I'm going to take the x antipartial of the first coordinate. I'm going to take the y antipartial of the second coordinate. I'm going to take the z antipartial of the third coordinate. Don't forget to say plus c. In particular, don't forget that your c's are now partial constants, aka functions of a certain sort. And the game begins. I'm looking for a function that's equal to all three of these things. And don't judge too quickly now. It's tempting to say, here, let's get the answer off of here. It's tempting to say, well, they're not equal because, look, they're different formulas. Right? But keep in mind, these partial constant functions, these can be anything at all as long as they're only functions of the correct variables. Right? And so, for example, it's tempting to say, look, there's an x squared y, there's an x squared y, but there is no x squared y right there, so we lose. But we don't, because maybe that's x squared y. Right? And then likewise, there's an xz, there's an xz, but there's no xz there. Okay, right, but maybe this is xz. Perfectly legit. There's nothing wrong with that at all. And then likewise, minus yz squared, and you know there's nothing wrong with that being minus yz squared. And so in fact, green, blue, orange, all three of those functions are equal to green plus blue plus orange. So that's our anti-gradient. And we win. Everybody happy? Okay. So that's how the game's played. And And by the way, the exact particulars and when will you need, sometimes you don't need these partial constants at all. You can just call them 0 and it's all good. But sometimes you do. So it'll play out a little bit differently every time. Okay, here's a two-dimensional example, and I'm going to return back to this vector field here that you'll recall that we just got through showing does not have an anti-gradient. Right? Remember, we computed the curl. It wasn't 0. Therefore, we know there is no anti-curl. No anti-gradient. So, okay, there is no anti-gradient, but what if I play the game? I better not win. I better not find an anti-gradient because we know there isn't one. That would be bad, right? So how will the game fail? What does it look like when the game fails? And I certainly hope that the game fails here. So let's play that out. Again, we take the first coordinate and we do an x antipartial. We take the second coordinate and we do a y antipartial. And you compute, and don't forget your additive constants. And here is the game. These are the two things that I need to be equal to each other. And go. Anybody see how to win that game? Can anybody find reasonable choices of C1, only a function of y, mind you. C2, only a function of x, that will make these two things equal to each other. And I don't think you can. Give it a try if you want, but I think you're going to lose. Does that make sense? Okay. All right, so that's what the game will look like. You will just not be able to make the pieces fit together. It's just not going to work, and that's how that'll play out. Okay, so that finishes Chapter 6 for us, and we are going to move on now to Chapter 7. Again, Chapter 7 is about, largely anyway, the three-dimensional version of the stuff we've already kind of done pretty much all the two-dimensional stuff we're going to talk about. We're going to have to define various new objects, various new constructions. Surface integrals is going to be a big one. And in order to be able to define surface integrals, we're going to have to be able to talk about parametric surfaces. And by the way, quick reminder, how did we define line integrals? Well, with parametric curves. So this is the analogous thing. We would expect to need parametric surfaces to be able to define surface integrals. So here we go. It's exactly what you would think it is. Remember, a parametric curve gives position as a function of one parameter. A parametric surface gives position as a function of two parameters. It's totally analogous. Instead of x, y, and z as functions of t alone, now it's going to be x, y, and z as functions of, well, maybe s and t. Okay. All right. Well, conveniently, we've actually already seen one of those. I'll remind y'all of this example. We did this back in section 1.5 or some version of this, and I made the observation that if you give me a point in a plane, you know what, bad color choice. Sorry, let me, I don't want to paint myself into a corner here. You give me a point x naught in the plane, and if you give me two vectors parallel to the plane, right, then I can add, some multiple of that first vector, and I can add some multiple of that second vector, and that will get me to anywhere I might want to get to in the plane. In other words, I can produce any point in the plane just by this construction based on a given starting point and a given pair of vectors parallel to the plane. Right, everybody remember there was I think it was maybe a homework exercise, or so we did something along these lines long ago. So, well, check it out. This is a parameterization. I mean, we didn't say that word at the time, or we may have. I don't think we said that word at the time, though. But it's a parameterization because it gives position in space, x, y, and z, as functions of two parameters, s and t. And that's what a parameterization is. So this is our first parametric surface. This is called a parametric plane. Okay. All right. Now, before we go into more examples, I do want to point out a shortcoming. Well, that's the wrong word. I want to point out the analogy breaks down a little bit. One of my favorite moves in thinking about parametric curves is to think of t as time. Right? It's very helpful. You're doing parametric curves, you think of t as time. Because if t is time, then a parametric curve is literally just telling you how to trace, as if with a pencil, how to draw your curve. Right? You can't really do that with parametric surfaces. I mean, how would I imagine both S and T being time? It doesn't make any sense. You can't have, I don't know, there may be some sci-fi movie out there where they have two different times, right? And that would be a really weird movie, right? And so maybe you can make some sense out of it, but in general, I don't think this is a very healthy way to think about parametric surfaces. So just let go of the idea of time and just think of this as position as a function of parameters. Okay, so now just like we did for parametric curves, I'm going to show you various methods for how to make them. Right? So we talked about how to, various tools for your toolbox for creating parameterizations of curves. And I'm going to show you now various tools for your toolbox for making parametric surfaces. Starting with my favorite, the easiest one, very often the best one for many purposes anyway, and it's called the graph parameterization. Y'all may recall we had a graph parameterization for parametric curves. It applies to graphs. Now, here we have a graph surface, whereas previously we were talking about a graph curve, right? Because parametric curves. So a little bit different. This is a surface in space as opposed to a curve in the plane, but it's going to be the same basic idea. The same basic idea, which is look at your input variables and let those be your parameters. It's as simple as that. If you have a graph, if you have one variable written as a function of the other two, whatever those two input variables are, let those be your parameters. Everything will just fall into place. So here's an example. Notice in this example I have conveniently z is a function of x and y. So x and y are indeed my input variables. I'm going to let x and y, therefore, be my parameters, s and t. Go ahead and write that. Go ahead and put that in your forming parameterization. And now, how are we gonna figure out what z is? Well, I mean, it's kind of, we don't even really have any choice in the matter. If s and t are x and y, you plug those right into there, into your formula for z, and that tells you what z has to be. Again, there's nothing to figure out. It's just a matter of plugging in and seeing how your hand has been forced to give you the right answer. That's what z is, yeah.
I know S and T are like the standard notation, but are we allowed to use different notation?
Well, yeah.
My S's look like 5s.
Oh, yeah. Of course, yeah, I have that same problem, honestly. I've been working on that problem for 30 years. And I think I'm making progress. But now I have a different problem that my 4s are starting to look like my Ys. But here's the other problem. A lot of people like to talk about the parameters as being U and V. Well, those are like the two most similar letters, right? Yeah, totally. So they should call them, I don't know, like M and Q. All right. Right. Yeah. Yeah. But I am not married to any letter choices. Yeah, absolutely. Yeah, right. Okay. So now you'll notice that in the example that I showed, or in the way I stated this, and in the example that I showed, it was z that was a function of x and y, and that doesn't have to be. There's nothing magical about alphabetical order, right? So it could be instead. Maybe y is a function of x and z. And if that's how it plays out, that's cool. Whatever. Just whatever are your input variables, make those your parameters. So you'll notice in this algebra down here, I can solve for y. And by the way, sure is nice that I can solve for y, because I definitely can't solve for z. Right? Try to solve for z in this equation, not going to work. Likewise, x. Can't solve for x either. But we can totally solve for y, thus making y a function of x and z. And that makes x and z my parameters. Go ahead and put that in your emerging formula that you're making for your parametric surface. And then, again, at that point, you have no remaining choice in the matter. Just do what you have to do. And in particular, if x is s and z is t, then that pretty much forces y to be this. And game over, we have a parameterization of that surface. Everybody see how that worked? Everybody note the analogy. Note how really similar this is to parametric curves, right? The graph parameterization for parametric curves. It's the same idea, just one dimension up. Okay. All right. By the way, you don't even have to stick to rectangular coordinates. Now, when you make a parameterization, it is understood that a parameterization means you want to solve for the rectangular coordinates. Yes, that's true. But you don't have to have solved for one of the rectangular coordinates. If you have solved for one of the other coordinates, let's say a spherical coordinate, just write down your conversion formulas. Just first thing, write down your conversion formulas. And then take whichever, let's say, spherical coordinate that you've solved for. Here I have rho solved for as a function of phi and theta. No theta is visible, but that's cool. It's just, partial constant with respect to theta. That's fine. Just take that, plug it in. Everywhere you see a rho, plug in your formula. And as desired, we have position, rectangular position, as a function of two parameters. And it just happens to be that now my two parameters are phi and theta. Which, again, regrettably similar looking. But, oh well. Everybody happy? Okay. All right. Let's see here. Probably the last thing we're going to be able to do today. Let's see, how much time do I have left? Oh, gosh. Okay. Yeah, not much, but let's do a little bit. I have enough time to cross this out. Y'all don't have to look at this. This is a cool example. Do y'all remember back in whenever it was we were doing parameterizations in the first place? There was that one with the bicycle wheel with the reflector on it, and it makes this herky-jerky pattern as it rolls down the street, right? And we can actually parameterize that pattern by basically using vector algebra. We turn a hard problem into a sum of simpler problems. This is a surface parameterization sort of version of that basic idea. But it doesn't come up very much. I think this is a fun example. It's a nice exercise that relates various different ideas, but ultimately This is a deep pull. It doesn't come up very often. So as behind as we are, I am going to remove this from your responsibility for this semester, and we will draw the line right here and pick up here on Monday. Y'all have a good weekend. See you later. Don't forget about attendance if I didn't already get you.